The multiverse of theoretical physics is an outcome of mathematical necessity, grounded in the behavior of subatomic particles rather than cinematic fantasy. It emerges from the same equations used to predict the reality we experience every day. This shift began in the 1920s, as physicists realized that subatomic particles do not possess definite locations until the moment they are measured. Until that observation, particles exist in superposition. Defined by the Schrödinger equation, a particle acts like a diffuse, overlapping fog of all possible states simultaneously. At its most basic level, the universe is built of chaotic mathematical probabilities rather than solid, predictable objects. Yet our daily experience is concrete. A weather forecast might list a 75% chance of sun, but the day itself results in only one definite outcome. This creates the measurement problem. Physics struggles to explain how a system transitions from a mixture of infinite possibilities to a single solid state just because someone looks at it. The historical consensus, known as the Copenhagen Interpretation, suggests that unobserved probabilities simply vanish. In this view, the wave function collapses the moment a measurement occurs. But this collapse has no mathematical basis. It represents a massive, unexplained gap in the laws of physics that standard theories cannot bridge. Currently, our understanding of physics lacks a proven mechanism to explain how the probability of the universe solidifies into the reality we see. In the 1950s, physicist Hugh Everett proposed a solution that removed the need for a collapse. He suggested the wave function never actually disappears. In Everett's view, the universe splits. Every possible outcome is realized in a separate reality. Take Schrödinger's cat. It is neither dead nor alive. The universe divides into one branch where it survives and a parallel branch where it dies. This interpretation means that every quantum event creates a new physical universe, vastly expanding the definition of existence. If the universe is constantly branching into alternate realities, why do we experience only one? The answer involves decoherence. This is the process where quantum objects lose their overlapping states as soon as they interact with the air, light, or heat around them. This interaction causes a massive, irreversible entanglement with the environment, acting as the mechanism forcing the split between worlds. Once decoherence occurs, these new branches become mathematically isolated. They are locked away from one another, making any future interaction impossible. We live inside one single, decoherent branch of reality, permanently separated from the infinite variations that are occurring simultaneously. These parallel universes are not located in deep space. No telescope will ever see them because they occupy no physical coordinates. They exist simultaneously with our own world, embedded within a high-dimensional mathematical structure. This is the universal wave function, a single equation that encodes every possible outcome of every quantum event in history. Our perception of a physical world is a byproduct of being inside the system. The true foundation of reality is pure mathematics. Our reality appears normal only because our specific branch has fully decohered, hiding the underlying quantum complexity from our senses. Everett's theory suggests our universe lacks any unique status. We are one of countless, random, mathematically inevitable outcomes playing out in parallel. The many worlds interpretation leaves the human experience as a localized, isolated fragment of a much larger, unobservable equation. In Part 1, we explored the vanishingly tiny realm of quantum mechanics, where reality acts as a blur of probabilities. Now, we are pulling back to look at the immense scale of physical space. For decades, the baseline model for the origin of the cosmos has relied on a concept called inflation. This model defines the Big Bang as an event of stupendous exponential stretching, a process that smoothed out the fabric of our universe into its current form. But cosmologists ran into a mathematical anomaly with this model. There is no physical requirement for this rapid stretching to stop everywhere all at once. This points to a mechanism known as eternal inflation. It proposes that the stretching of spacetime is an endless, ongoing reaction happening far outside our observable boundaries. Under this theory, our universe is a localized pocket. We exist in a quiet patch where the inflation switch flipped off, allowing energy to cool down and matter to coalesce. Everything we can see, Every galaxy, star, and planet is a single, solitary bubble floating within an infinite, violently expanding cosmic froth. Because the space between these cosmic bubbles continues to actively inflate, they are pushed apart much faster than light can travel. You could travel endlessly and never cross the gap to reach one. And if you could, you likely wouldn't survive the trip. String theory suggests that the foundational blueprints of reality, constants like the strength of gravity or the speed of light, take on entirely different rules in different bubbles. The math of string theory allows for at least 10 to the power of 500 possible configurations of physical laws. Most of those configurations are brutally unstable. The resulting physics cannot support a stable pocket of spacetime, causing those bubbles to instantly pop or decay into chaotic voids. The physics of the multiverse describes a sprawling graveyard of incompatible alien realities, far removed from the character-driven timelines of science fiction. This presents a massive epistemological wall. How do scientists find empirical evidence for realities that are moving away from us faster than the speed of light? The answer might lie in a collision. If two bubble universes spawned close enough together in the early cosmic froth, they could have physically crashed into each other before the expanding space had time to hurl them apart. To find evidence of those crashes, cosmologists look at the cosmic microwave background, a heat map capturing the Big Bang's afterglow. Cambridge researchers designed an algorithm to comb this data, hunting for circle-shaped scars left by another universe's impact. The algorithm successfully identified 4 patches of the sky compatible with the shape of a collision. However, the exact rate at which these bubbles form is still too uncertain to call these marks definitive proof. Because we cannot rewind time to observe the precise mechanics of bubble formation in the early cosmos, physicists are attempting to build physical replicas right here on Earth. This is an experimental setup at Cambridge University, explicitly designed to simulate the birth of a universe. The team uses lasers to chill potassium atoms down to a fraction of a degree above absolute zero. This creates an exotic state of matter called a Bose-Einstein condensate, acting as a direct proxy for the unstable vacuum of early space. Under these conditions, the researchers can observe false vacuum decay in real time. They watch microscopic bubbles of lower energy states spontaneously form and expand within the condensate, perfectly mimicking how our own universe bubbled into existence. By accurately modeling how these bubbles form and crash together on a lab bench, scientists are dragging the multiverse hypothesis out of abstract philosophy and turning it into testable empirical science. This leaves us with a massive existential question. If the vast majority of those 10 to the power of 500 configurations result in dead, unstable voids, why is our universe perfectly calibrated to sustain matter, chemistry, and life? Physicists call this the fine-tuning paradox. If you alter the physical constants of our reality by even a fraction of a percent, the intricate structures required to build stars and DNA become impossible. The multiverse offers a statistical solution known as the anthropic principle. In an endlessly expanding space, rolling the dice an infinite amount of times, a bubble with the exact conditions necessary for life is guaranteed to occur eventually. Humanity exists in this specific, finely tuned universe because it is one of the only outcomes where observers can exist at all. Our understanding of reality is constantly expanding outward. What we originally modeled as a single static universe looks increasingly like a minor fraction of an infinite, ongoing reaction. Under the eternal inflation model, our universe is completely sealed off, floating endlessly away from countless other realities we will never touch. We occupy the position of a beautiful,